After a 6-year journey together, ESA's Mercury planetary orbiter and Japan's Mercury magnetospheric orbiter will reach the planet and encounter extreme conditions. Both spacecraft will be exposed to the full glare of the Sun only some 60 million kilometers away, and have required major design innovations and technological developments.
Bringing a spacecraft into Mercury orbit is the biggest challenge because of the thermal environment. It has temperatures on the outside up to 400 degrees centigrade, so it requires new technology for all the materials that are used on the outside of the spacecraft in order to sustain the heat.
White ceramic-based material, as found in firemen's jackets, and many layers of wafer-thin metallic insulation will double-wrap the spacecraft, whose electronics must remain around 20 to 40 degrees. Covering an entire side of the planetary orbiter, a sophisticated radiator with a Venetian blind system will evacuate any excess heat and ward off radiation from the planet itself.
When looked from the planet, offer highly reflective surface. So the radiation from the planet basically bounces off from these Venetian blinds. At the same time, the radiator can see space through the Venetian blinds and then radiate its heat into space.
The biggest challenge, though, has been the design of the spacecraft's solar array. Unlike Rosetta straining to catch sunlight, BepiColombo's power generators require only a small fraction of it. In such an environment, without new materials or structures, standard solar panels would rapidly be degraded, if not burn.
We have also to use not only solar cells in the panel, but also mirror to get rid of the most of the light that enters into the panel. Even if I put H on the solar array, so the solar cell, so more or less is not exposed to the sunlight, but due to the infrared of the planet, the temperature could reach even 140, 150 degrees centigrade.
The tests just completed have seen the Japanese orbiter and its European-made protective sun shield placed in ESA's large solar simulator in Noordwijk. This unique European test facility had to be upgraded with even more powerful lamps and specially focused mirrors to recreate the intense thermal conditions around Mercury.
It is the very first time that we see on a spacecraft scale what is the behavior of the thermal system, and in particular the behavior of the high temperature thermal blankets. How much heat do we get through the blankets into the spacecraft?
These tests constitute a major step for ESA engineers and the prime contractor EADS Astrium, also closely followed by the mission scientists. Upon the spacecraft's survival, of course, depend the science data from the dozen instruments on the European probe and those of its Japanese partner to understand, for instance, the planet's magnetic fields.
We can have gradient measurements from one spacecraft to the others, or two spacecraft in an orbit around the planet, where we have 2 points actually, and build gradients within the magnetosphere in order to better characterize the magnetic field.
The scientists have many other questions about Mercury: the nature of its core, is it liquid or solid, the origin of the many long scarps across its surface, and paradox of this intensely hot planet, the eventual presence of water and ice at its poles.